All right, party people. It is Tuesday the 6th, and we are rolling through chapter 5 here. So I sat down this weekend and I really read carefully through this chapter. There is a lot of information here, and so I kind of planned out my lectures, slowing us down just a little bit to make sure that we're getting this. This is a lot of very important information. We're talking about ionic bonding, covalent bonding, and how to represent those things. Lewis structures are some of the sort of central information that we're trying to get you guys to have from chemistry that sticks with you. So I think I've mentioned that this is a pretty central chapter, but I just was hit by that again when I was reading through this. There's so many topics that just I think of as very central to chemistry. So we're going to take our time, and it may feel like we're going fast, but I was hoping to get through chapter 6 so we could finish the whole book this year. Get through chapter 6 this semester. I don't think that's going to happen. If you've looked at your 4th, 8th planning, basically we're going to finish chapter 5, do a lab, and that is going to be it for this semester, other than we got a chapter 5 test, we got a chapter 5 quiz, you got your lab report, and your final exam. But we're not going to cover any material past chapter 5. There's just no way we could really get to it all and really dive in and understand some of this stuff. And looking at some of y'all's homework, we're going to need to spend a little bit more time even on what we've already covered. So what I want to do, this is today's lecture right here through 5.3.2. Okay, and I normally don't even break stuff down into little sub-chapters, but we just got enough stuff that it warrants that. And then next time we'll lecture on 5.3.3, 0.4, and 0.5, and we'll have a quiz on 5.1 and 5.2. Okay, and then we'll come back next Tuesday and I'll lecture on 5.3.6. You'll have a Lewis structure practice. You don't even know what that is yet, unless you've read and annotated and absorbed everything from your chapter here. And that's awesome if you have, but you may have a little bit of an idea what a Lewis structure is. We're going to really get into that. And then next Thursday, I'm going to lecture 5.3.7, 0.8, 0.9, 0.10, 5.4.1, and 0.2, and that's going to take us to the end of the chapter. So we've got 4 more days of lecture just to get through this chapter. We'll have a quiz on Thursday, and then I think I set the test. What did I set it for? The test is, we'll have a review and then a test after Thanksgiving break. Okay, so we'll have Thanksgiving break week after next, and then we'll have a little bit of, we'll get you guys back in the groove before we throw a test. Maybe we'll be able to meet that Monday when you come back from Thanksgiving break. We'll try and plan that and schedule that to meet up and kind of get everybody back face to face. We can work through some problems because there's a lot of problem working involved in this. Then we'll have experiment 3, and we'll do some final exam test review because we'll have a semester test, and that'll be it for this semester. All right, and so what I wanted to cover today, bell ringer review. I hope that you guys have just finished that with Mrs. Barron. If not, pause me. Tried to feel it, couldn't feel if you paused me or not. All right, then we're going to go, we're going to work through some of these problems to let you know how you work them. And then we're going to move on and start some new material here. All right, so y'all get out your books, if you will. Let me move you back up a little bit. There's my tea. All right, there we go, we're back. All right, come on, camera. Focus. Oop, not gonna autofocus for me. There we go, better. Okay. All right. So distinguish between ionic and covalent bonds. You guys can do that. You can look up those answers. If I will actually send those answers to you. I'm making myself a note. Send homework answers. Okay. All right. So we're just going to work through these right here. So go ahead and get to page 147. Okay. And I'm going to be flipping between that and this chart right here. Okay. And I'll show you why in just a second. All right, so let's start, and I'm just going to turn this sideways, sorry, but that's what we got to do. Okay. All right, so how do we approach these? Okay. So if we're going to pair up, and now of course this is only true for ionic compounds, because covalent ones aren't, well, that's not true. Covalent ones go by this same way, but a lot of times you have more transition metals where it's harder to tell kind of what the oxidation states are and why they act the way they do. So for right now, we're just going to stick with this very simple setup here. So we're going to have SR and BR. All right. So first off, we're going to see, do we know it's one of the ones that's just follows the basic rules? So we know that these are all +1, all +2, all -1, all -2. These are -3, and I don't know about these down here, but these for sure are -3. Okay, so we know that this guy is always strontium. It's 38. It's a +1 and a -1, so they just fit together. SRBR. Okay. And in ionic compounds, we don't ever have to worry if this is 2 and 2 or 3 and 3, because these are all just going to be one guy giving up electrons to the other guy. Okay? All right, so next is going to be magnesium and oxygen. Okay? Mg is a 2 plus, 1, 2. Oxygen is a 2 minus, +2, -2. So that's just MgO. Okay, so straightforward. All right, so what do we do with some of these other ones? So, well, we'll just go ahead and do C in order. Okay. Cl. Okay, so this guy we know, we don't have to look it up because we're given this Roman numeral right here. We know he's a +2. And chlorine, we know because it's a halogen, is just a -1. And so what? We've got to have 2 of these guys to balance out the charge of this one. Remember, we want 0 overall. So we know that it's going to be CuCl, and we got to have 2 of these guys. Okay? Because this is going to be then 2 times the -1 and a +2. We have +2 -2 equaling 0 overall. So we're good. We're balanced. Okay? All right. So some of these, though, are not clear. These transition metals. All right. So let's look right here. I was a little thrown off by this, but Ag and Se. All right. Now, so we don't have enough information just from this right here to answer this question. We know Se is a -1, -2. Okay, but what's Ag? We know that these transition metals are all over the place with their oxidation states. Okay, I'm sure there's an explanation for some of them. But if you look at these right here, you can see this small number at the very bottom, and we see that that's the common oxidation states. All right, now that doesn't say the only oxidation states, because things are kind of weird here in these transition metals, but those are the commonest, the most common. All right, we see they're all over the place. What do we have? +3, +4, +4, +5, +3, +6. So we got a 6 there. 2, 4, 2, 3, 2, 3, 2, 1, 2, 2. Okay, so we don't know what they are. Okay, but the one we're given here, Ag, we see that it only has 1 common oxidation state, and that is a +1. So that's going to give us enough information to assume, for our homework purposes anyway, that that's what he is. Okay, so what do we need? We got a -2, a +1, so this has got to be, we've got to have 2 of the +1s to balance out the 2 minus, and that's your answer there, Ag2 selenium. So what will we call that? That's silver selenide, I believe, is what we would call that. Okay? All right, so we're not going to work through every one of these, but so some of these, they can be a little confusing. CO3, cobalt 3, and oxygen. Okay, so what is this? This is a 2 minus, and this is, as we're seeing, is a +3. Okay, so some people remember this. We know we're going to have cobalt oxide. They bring the oxidation states, they bring them across like that. Okay, and so what do we have? We have CO2O3. Okay, that's correct. Okay, so what does that give us? We got 2 cobalt, so that's a +6 over here. 3 oxygen, that's a -6. Good, we equal out to 0. Okay, I don't know if that helps people to do this cross thing. I always thought that was just kind of more confusing than anything else, but whatever. That's fine if that's helpful to you, that you just bring them down like that. You just also can work your way up. You can see, you could write it like this, cobalt, oxygen. You know, it's a +3 -2. That's not enough, so maybe we put a 2 here. What's that? Now that's a -4 and a +3. It's too many. So now we do a 2 here. Now we got a +6 -4, still not balanced. So then we put a 3, and we end up at CO2O3. Whatever method you want to do to get those to balance out is perfectly fine. The math's not going to get any harder than a 2 and a 3, or maybe a 5 and a 3, maybe. I don't even know about that so much. Okay, so the process is, you check it out. If it's one of these that we know what it is, we just go ahead and grab that oxidation state. If we don't know what it is, you look right here and you look at this bottom oxidation state deal. Okay? And notice, I mean, you notice right here, you have -1, -1, -1, -1. This has the same information. There's nothing different here than what we know. All of these are +1s. All of these are +2s. All of these are -1s, -2s, -3s. And I was right that these aren't just -3s. Notice that these are these transition metals here. I mean, not transition, metalloids here tend to be a plus, even though down here they get to be. So these are just weird. That you can count on your non-metals and your 1s and 2s right here, and then you got to look up basically everything else because you don't know what it is, and you'll never be expected to know that. So don't worry about that. Okay. All right. That's all I wanted to do for homework here. So let's roll on, and we're going to be picking up in 5.2.3. So flip back to 5.2.3. You can see my crazy notes in here. Okay. 5.2.3. Oh, also, I wanted to come back to this. I kind of blew this off last time, and I shouldn't have done that. I want you to know this. This is called the stock system. I guess that's just somebody's last name. I know nothing more than what this chapter says. And just remember that this has got, these are the oxidation states. Okay, they're given to you. Okay. And we use them, once you use that, you just use them like anything else, okay? But then you've got this other thing that's right here, and they call them ferrous, ferric. Ferrous is the 2+, ferric is the 3+. I mean, tell me how much better is this one, okay? goes ahead and tells you. You don't have to fool with remembering, oh, which is ferric is 3 or 2 or what is it? You know, I'm not going to test you on this. Okay, you will need to know this for sure. Okay. I also you got enough stuff that we're fixing to talk about that you're going to need to actually memorize. So we're not going to fool with any of this. You just need to have that kind of stored in the back of your mind just for your own edification. That if you see something that says it's ferrous oxide, you know it's the lower oxidation state. Whatever. Okay. So I don't want to blow it off because it is still used by some people. But this is the one we'll be using because this is the only one I've ever studied in chemistry when things are multivalent, which brings up that, go ahead and underline that. Guess what? That's going to show up on a quiz or test sometime, okay? Multivalent, what does that mean? It means it has different valences that it takes or different oxidation states that it has. And as we saw just a second ago, a lot of those transition metals have those multiple states, okay? That's all I needed from that one. All right, so now we're going to start our new lecture here. Energy in ionic bonds. Okay, so this is kind of interesting because I've never really gone through this calculation before, and I've had high school chemistry, college chemistry again, organic chemistry. So I just somehow I missed this whole topic, and I don't want you guys to miss it too. And so I did not realize that there is a whole lot of energy actually tied up in the ionic bonds. All right, and so that's energy that's literally locked up in there. And so I just want to take you through this little calculation right here. Maybe you guys are already way ahead of me here. It's definitely possible. But I wanted to help you think through that as we lecture through here, so that you kind of are able to track that energy in a very physical sort of way that is, I don't know. I always kind of think chemistry sort of gets a bad rap as like sort of magical. We just sort of memorize these weird rules, and it doesn't really make sense on any fundamental level. And maybe that's just me and my bad chemistry education that I had, but I don't want you guys to feel that way. And so I want to take you through this step by step, and I want you to understand where each of these numbers comes from and how we can add them up, and then we can use that to make some conclusions. Like everything else in chemistry, they're going to be indirect conclusions, but they don't have to be mysterious conclusions, okay? They're just indirect, and we have to use logic, and we know that that logic works and that it's true because we're able to do what I would term pretty magical things with chemistry, okay? So we're able to do all sorts of things with all sorts of products. Plastics are just a marvel of chemistry that we wouldn't be able to have if these guys hadn't done some really good logical thinking here. So let's dive into these numbers really fast. And you can write these down separately, or you can just kind of follow along and sort of maybe underline some of the high points here. All right. So remember, we're just talking about sodium chloride. Not remember. We are talking about sodium chloride. Remember that is a +1 -1 deal, which means that we've got our sodium, and I'm just going to draw this. That's a little electron there. And remember, he's going to actually migrate over to our chlorine, and it's going to plug a hole that's there in that happy octet shell. Okay, remember that, all right? So what should we know? We should have the, what is it to remove an electron? That's our ionization energy. First ionization energy, remember. Y'all got that on your test there. Okay. Oh, also, you guys should get that back today. They're all graded. The only person whose I have not graded is Miss Miller's, who was sick and has taken it, and it got left at the school. So I'm going to grade that as soon as Miss Anlauer or Miss Forster brings it back to me. So sorry about that, Julia. If you guys haven't gotten those back yet, and Ms. Barron has them, she can pause me, hand those out. Y'all can talk for a minute about those. Or if y'all already have given those back and y'all have any questions, also feel free to pause me. I want to encourage y'all to understand that. But take some time, correct those, get them back to me so I can fix or give you those points back, or the quarter of the points back, or whatever. All right. So the first ionization energy right here, and then the electron affinity here. All right. So we'll call this the sodium first ionization energy, and then the chlorine first electron affinity. Okay. Remember, this is what the energy it takes to pull that electron out of there. This one is what energy is released when that electron comes into an atom. All right, and we're told right here, and we could look these up in charts. People have empirically done this. Okay, they've empirically figured out these values. Okay, so what do we have? Ionization energy. So that's 5.14 electron volts. Okay, remember that's convertible into joules, which is our SI unit, but it's very small, so we use these, which is nice. Okay, and then the energy released when this guy falls into place in the chlorine is 3.61 electron volts. Okay, so remember this is energy in, and this is energy out. Okay, I'm not going to use positives and negatives, but we could. Okay. All right, so he says we've got a problem. We've got to put in 5.14 and we only get out 3.61. How does this reaction ever happen? Okay, and he says for this to actually happen, they must be vaporized. Okay, so we also have to put into vaporize 1.12 electron volts. More trouble. 5.14 in, only 3.61 out. Another 1.12 in. Okay? And then we need to separate Cl2 into Cl minus and Cl minus, which is another 1.25 electron volts we got to put in. Okay, so we have 5.14 in, now I am going to use these negatives, 3.61 out, 1.12 in, 1.25 in. Okay, and what does that equal? 5.14 plus 1.12 plus 1.25, and I need to get my calculator because I'm slow. 5.14 minus 3.61 plus 1.12 plus 1.25. All right, so that means we need to put, that's not right. 7.51 minus 3.61. No. All right. So we have to put in or per individual NaCl. Okay, so that's a lot. We're losing that energy in there. All right, so this is sort of a very real deal. This energy going in. If you were doing thermochemistry, you'd have like a special insulated deal that's way better insulated than any Yeti ever thought about being. And you would actually figure out how much the heat is changing here when you do each one of these individual ones. Again, you'd have to have super good thermometers, super good insulated deals. All right. So anyway, the point is we're losing 3.9 electron volts at the end of the day, each one of these compounds. Like an individual NaCl molecule requires this much. All right. And so What does he say? Just we imagine that they do stuff far apart at the very end of the page, imagining it in energy terms. There's a whopping amount of energy released when all the cations and anions come crashing together. So they're out there, the Na is way over here, and the Cl is way down here, and they go, and that kinetic energy gets translated into that extra energy. Okay? And it actually gives off enough energy, that kinetic does, it gives off enough energy to where there's some actually bound up in the lattice energy itself. Okay? All right, so I don't want to do too much more with that, okay? Other than, like him, I feel like we should point out this is really interesting right here, the way he goes through this. This is the kind of nerdy calculation I would do, or maybe even ask you guys to do in a bell ringer or something. You know, he goes through this whole deal, and he tells you that in 1 mole, we could basically leave a 60-watt light bulb, and, you know, we or whoever's your physics teacher for next year will get into watts and stuff, and you'll get a much better sense for that. But it could run a light bulb 3.6 hours, okay? So, and it's a 1/4 cup of salt. That's not very much. That's a lot of energy tied up in that. All right, and moving on through here, you can see I just marked here, I don't understand this here. He says, since the water molecules are polar, they rush toward and surround the dissolved ions, releasing enough energy in the process. I don't understand what that means, so we're just going to trust him that we're going to return to this topic when we get to the chapter on solutions. All right, we'll have to learn that together because I don't, again, necessarily understand what that means. Okay, all right, very quickly, 5.2.4, hydrates simply means that there are literally water molecules inside this crystal lattice. Okay, so he gives you a pretty good diagram here, this 3D. So there are water molecules like tucked in there. Okay, now it's not wet. In fact, one of the things that we dissolved, I think, was actually a hydrate. Okay, in our lab, dissolved in our lab. I think it actually was a hydrate. And so they're powders, which is kind of weird because those water molecules are not dissolving it, but they're still in the structure there. Okay. Again, I don't know much about that. I think we're going to talk more about that in our next chapter, the actual structure itself. But just know that hydrates mean that water molecules are inside that crystal lattice. Okay. And we're using that word lattice. You guys have seen lattice work, like that, those thin wooden slats that you kind of cover up like the bottom of a deck with. They're kind of flimsy. You've seen it in a Home Depot maybe or whatever. That's the same thing we're talking about here. This lattice is this like structure that's mostly empty space. So scaffolding is a kind of lattice. It's got these thin poles, and you kind of walk along, but it's mostly empty space in between the things. All right, so that's the image I want you to have is a structure with space in between there. All right, intensive and extensive. Just I always thought this was kind of a weird distinction, but intensive is a bulk property, meaning the property does not depend on how much of the material is present. Okay, so brittleness, electrical conductivity, boiling point, and density. Color, reactivity, all those things are true for one atom or molecule as they are for a gallon of that substance or a cubic meter of that substance. So the amount of it doesn't matter. The color's the same whether you've got one piece of sand or a whole bucket full of sand. The density is the same whether you've got one bucket full of sand or the Empire State Building full of sand. The density is the same, all right? Those are intensive. They're intrinsic to that piece, okay? Extensive depends on how much material is present. I don't know how some... I mean, I guess I see how mass and volume are properties, but like obviously your mass depends on how much of the thing is there. So whatever. That's an extensive property. So you have more stuff, you have more mass. So I guess his point is that, or the science's point, because I learned that in chemistry too. The point is that you can't. Mass is fundamentally different from density in that I add more of a substance, I end up with more mass, but my density stays the same. Okay, or my electrical resistance stays the same. So that's a good, I guess, a good distinction to make. I don't really understand what you do with that other than know that those words are. So just know those words. All right. Physical properties, very quickly, we're going to move through here. All right, so he points out here helpfully that all these things, because we've moved charges, right? So we got a positive and a negative. Okay, blues are negative, golds are positive. And so think about all the forces they're all electrically attracting one another, and they're all squishing together as much as they can to do that close packing. They're put a bunch of balls in a box, and they're all going to fall down as much as they can and get as close as they can. All right, that's what they do here. And those things are a lot of forces holding them together. So what does that mean? Okay, strong electrical forces in the crystal lattice, brittleness. Okay, the tendency of a substance to shatter instead of bend when stressed. A great vocabulary word for you guys to know. Okay, so what's brittle? Glass is brittle. Okay, osteoporosis bones are brittle. He says they can flex to some extent. He says that's why we use quartz to regulate clocks. High enough stress, crystal lattice breaks apart. So whack a lump of iron with a hammer and you may put a dent in it. Whack any ionic compound with a hammer, including all the rock minerals. Okay, so lithium, sodium, potassium, whatever, and they will break apart. Okay, now we usually don't see salt, like a big thing of salt, but if you hit it, you just crumble to pieces. Okay, it can't handle that. All right. High melting point and high density are two other physical properties. Again, so high melting point, melting requires that this structure be broken down. So you got to put enough heat in to break that structure down and turn it into a liquid to overcome all those electrical things. And high density, they're pulled very tightly together, so they're packed very densely. And you can see the difference here. Look at these melting points. Good golly. 2,800 degrees Celsius. It's unbelievably high. What's water melt at? 0 degrees Celsius. Okay. All right. Covalent bonding. All right. The fundamental distinction of this chapter. All right. Listen up. Open your ears. Ionic bonds can be thought of as transferring electrons. They leave one and go to the other. They leave sodium and go to chlorine. Covalent does not transfer. Covalent shares. Ionic transfers, covalent shares. That is the fundamental distinction of this chapter, and you must understand that. Okay? All right, so then he goes into a nice, helpful deal here. Kind of takes us through what we're going to be using for the next couple of lessons. Okay? And those are Lewis symbols. Okay. All right, so what are those? They are just the symbol and how many valence electrons it has. Okay. All right. And then we have, I'm just going to do what he's got here. Oxygen. What's oxygen have? Well, we know that it's in, we look over on our deal. We know it's got 1, 2, 3, 4, 5, 6. It's got 6 valence electrons. And so the way we do it, well, it doesn't really matter how you do it, but I typically go 1, 2, 3, 4, 5, 6. Okay. Kind of reminds us about that doubling up thing. They don't like to do it unless they have to. The electrons don't like to double up unless they have to. All right. And then we see that, all right, so what? He's missing one right here, missing one right here. He needs 2. Hydrogen, remember, only wants 2. He doesn't want 8. Okay, so what they're going to do is they're going to arrange themselves to bring that H right here, that H right here. The oxygen is going to bring his. All right, and then we could draw those even closer to where they're like this. All right. So there's no transfer of electrons. They've moved themselves around so that they can share. All right, so this is a bond pair, a pair, pair, pair. Okay, so oxygen, full octet, and hydrogen has a full S subshell, which only holds 2 electrons. Okay, remember that hydrogen doesn't even have that P shell, and it would be unstable if you tried to force it, so it doesn't try to get 8. Okay, it wants to get 2. Helium's the same way, but it's already got 2, so he's not going to react with anything. Okay. All right. All right. You can see carbon dioxide. If y'all want to pause me and work through that, you can, but I'm already at 40 minutes here, so I'm going to zip on through here. Yeesh. Okay. Double pairs of electrons we see when we okay, y'all do pause me though and just go through that, Mrs. Barron, please, and take them through CO2 to show them what a double bond is. I'm worried I'm running long here, and if y'all don't have time, just I guess don't do that if you don't have time, but if you do have time, please do. Okay, so that's a double bond. There are also triple bonds. Okay, and you can check all those out right here. Y'all can talk through why those are triple bonds. All right, well, y'all can't talk through it. I will talk through triple bonds here. Okay, so why do they do that? Okay, so nitrogen, it's got 1, 2, 3, 4, 5 valence electrons. What happens? We got nitrogen, and he's got 1, 2, 3, 4, 5. Uh-oh, he's missing 1, 2, 3 to get a full thing. He finds another guy who's got 5, and they move together. Okay, so what happens? Now, what do we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's do this. All right, so we share 2, or we share a double bond here. All right. And what happens? Now we've got only 8 left to distribute. Well, we can do the math. We can distribute 4 around this guy, but he's still going to be short. 4 around this guy. He's still only going to have 6. So we put a second bond there, and they share it again. It's still not going to be enough. And they share a third bond. So that's 6, 7, 8, 7, 8. We've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. Okay, and the only way they both have 8, see, he has 8 here, and he has 8 here. The only way they're able to make 10 electrons do the work for both of them to have 8 is for them to share 6 electrons or 3 pairs. Okay, and you can see that a number of them have double bonds, and in the case of nitrogen, triple bonds for that to work out. Okay, you really just have to work with them a bunch, which is why I gave you a bunch for homework. All right, polyatomic ions and covalent molecules form polyatomic ions. Okay, poly, many, atoms, ions. So this name speaks for itself. So if I ask you that, don't freak out. Just look at the word and figure out what it means from its roots. Okay, and he doesn't actually state this right here all at once. So I do want to show you this. This is just a slightly modified definition from the back of the book, the glossary. Covalently bonded compound that carries a net charge, most often negative, but occasionally positive. Okay, so we're going to work a lot with these and really kind of get into this. I'll probably spend some time in the next lecture reviewing this. Yeah, I think we'll have some more time next time. This is your SO2. Okay, what do? You add up the valence electrons from sulfur, 4 oxygens. I'm sorry, sulfur and 4 oxygens. Okay, and you get 30. And we know, just empirically, you wouldn't know this just looking at the atom because you don't know how many electrons are in there. But they have given us the oxidation state here. Okay, they know it likes to bond with 2 positives, which means it likes to carry 2 extra electrons that it sucked off of maybe 2 sodiums. Okay, so we got to find place for 30 come from just the atoms that make this up and their valence electrons, and we know it's a 2-, so we have 32 total. We start putting them in there, and if you guys have time, you can pause me and work through that. Okay, and nitrate does the same thing. So you take all your valences, add them up, get the charge, add those extra electrons in there, okay, and then you draw it. Okay, and if everybody doesn't have an octet, if you're short some electrons to make that happen, try doubling up one of the bonds. Okay, all right, note that we've got one double bond right here. All right, so in addition, note these common polyatomic ions. You will need to know these, or at least some of these. I'm going to look at these and tell you which ones you're going to need to memorize. Ammonium, ammonia's NH3. Ammonium's got an extra hydrogen, so it's an ion. It brings that H plus into there. Okay. Ammonium, hydronium. We'll talk about this a good bit when we talk about acids and bases. Acetate, so acetic acid is CH3COOH, but that H comes off pretty easily, and so it likes to bond with other stuff. So we have maybe a sodium acetate, and that's a common thing, so that's important for us to know. Bicarbonate, sodium bicarbonate is baking soda. Chlorate, hydroxide, very important one right here. Nitrite, nitrate, permanganate, carbonate, chromate, sulfite, sulfate, phosphate. Okay, so we'll talk about which ones of these we need to memorize. I hated memorizing them. I really did, and I know you guys would hate memorizing them too if I forced you to memorize them all, but I feel like we need to know some of these, so just resign yourself to your fate on that one. I'm not telling you we're going to memorize them all, but I'm also not telling you we're not going to memorize them all, so just roll with me on that one. Okay. Notice that only 2 of these are positive and all the rest are negative. Okay, that just seems to be the way that they like to bond to become negative. Okay. All right, so we are going to stop right there. I've rambled on too long already. All right, and then so next time we're going to have a quiz on just these first 5.1 and 5.2. Okay, so none of the real, you're not going to have to go home and memorize a bunch of stuff by Thursday. Okay, so 5.1 and 5.2. Look at your vocab. Look at the homework I asked you to do. You basically need to be really familiar with ionic compounds, how to make them, how they're named, how to figure out how many of each of the elements is in them, what's going on with ionic bonding, aka a transfer of electrons. Okay, reread back through over here these mechanisms, these basic ones. We talked about that. The different kinds of bonding. Basically, anything that I've got highlighted here or underlined here, we want to be a little bit familiar with because it could show up. Okay, so 5.1 and 5.2, you'll have a quiz. That'll be 30 points. Nothing surprising there, but you need to gear up for it. Go ahead and look over 5.1 and 5.2 tonight and Wednesday night, okay? You'll be doing your homework for Thursday as well, and that won't be on the quiz, but you'll be in chemistry, okay? You'll be marinating in it, okay? And like I said, I'm not going to test you on this. I'm not going to quiz you on the sorry, you can't see that, on the Latin ones here, okay? We're not. Don't worry about that. Don't try to memorize that table down there because you don't need to. Okay. All right. Good. Y'all feel free to let me know about questions. I'll be grading your lab reports just as quickly as I can, although I don't know that it's going to happen before this weekend, just to be honest about my week. But I'll be pushing on that as quickly as I can. I want you guys to get those back so we can move on. I think that's it. Oh, also, this is not for the quiz, but just I forgot to mention it. 7 elements that form diatomic molecules right here. 1, 2, 3, 4, 5, 6, 7. Note those. Circle that. Underline whatever you need to do, because that's going to be helpful when we interact with things like that. You know how that hydrogen's coming in because it's always coming in as an H2. And diatomic just means that they bond with themselves, N2, O2, F2, Cl2, Br2, I2. Okay? If they're hanging around as just iodine gas or chlorine gas, it's Cl2. It's not just hanging out as a single solitary Cl or a bunch of single solitary Cls. They're bonded together. All right? I'm really done now. Y'all work some examples. If you've got some time, y'all review some together for your quiz. I can't imagine you got a whole lot of time left, though. All right. Thanks.